Hi, BC Calc. We are ready to get rolling for the 2020-2021 school year. We're going to start with day one, which is in your packet that was provided to you. Now, one quick note, and I believe I should have mentioned this in class, this packet takes us through the first 10 days of notes. I can't promise that we'll always have a packet just like this. I'm just going to play around with, some different ways of getting new materials in the beginning. I thought it'd be easiest just to start this way, and then we'll kind of see what happens from there. But if you want to take out the packet, turn to that first page. Let me plug in here so we can see what we're working on. I'll tell you that day one is going to be out of chapter 2 in your textbook. So it's a little bit odd because I would say the way our units are structured is we will go through the order of the textbook, but unit 1 is really chapter 2, and unit 2 is sort of chapter 3. So to avoid confusion, I actually might just label these as the different chapters that they correspond with, but we are pretty much picking up with chapter 2 since your summer homework assignment is primarily from chapter 1 and things that you would have learned in pre-calc honors last year. So I'm hoping this stuff kind of looks familiar. So we're going to start by some evaluating limit methods, and there are 3 main ways in which we can evaluate limits, one of them being algebraically. So algebraically is basically just plug and chug, right? So you would plug in a 2 for the x in this expression, see what happens, and kind of go from there. We can also evaluate limits graphically. So there's a little bit of a caveat to that, but we would basically look as x approaches some value, in this case as x approaches 2, are we getting closer and closer to some specific y value? So that would be a graphical approach. And then finally, we will take a look at a numerical approach. So numerically would be really just by testing some values in a table-like format, whereas x gets really, really close to 2. We'll analyze the y values and determine if the limit exists. So if we take a look at these 3 approaches just for this first example, let's take a look at algebraically first. The limit as x goes to 2 of x squared minus 4 over x minus 2. And you can see that if I just follow that technique of plugging in 2 to the top and bottom, 2 squared minus 4 is going to be 0, and then 2 minus 2 is also 0. And I believe that you may have learned that form last year. It's called an indeterminate form. I think even Siri knows that. Siri, what's 0 divided by 0?
Imagine that you have 0 cookies, and you split them evenly among 0 friends. How many cookies does each person get? See, it doesn't make sense. And Cookie Monster is sad that there are no cookies. And you are sad that you have no friends.
So sad, guys. All right, so indeterminate is the form that we see if we get 0 over 0. So it's not that the limit does not exist. It's not that the answer is 0. We have to do something else to determine what the limit is. Okay, so 0 over 0 is kind of a question mark at this point. We don't know if there's a limit that exists or not. So the way we're going to approach this is, hopefully you're seeing it already, just factor at the top. So we get x plus 2 times x minus 2. And what that winds up doing is the x minus 2 factors top and bottom cancel. So we're now taking the limit as x approaches 2 for the quantity x plus 2. So great, now the algebraic approach is take that 2, plug it in for x. So we get 2 plus 2, which is 4. Okay, the limit as x approaches 2 is not 0 and not 0 over 0 anymore, it's actually 4. And that is the algebraic approach to this process. So then if I kind of draw a line here to give myself some room for the graphical method, graphically, if I want to think about what this looks like, you can certainly type it in the calculator. The calculator does an okay job showing what this looks like, but it does avoid one key piece. And it's the fact that I'm going to graph the function x plus 2, but there's going to be something weird happening at x equals 2. Maybe you remember what that is from last year. So if I graph x plus 2, that's a linear function with a y-intercept at 2. So we're going to rise 1 and run 1. And then when I get to x equals 2, the y value we know is 4, but there's going to be a hole in the graph. There's going to be an open circle there. So you really have to make sure you account for that. And on your calculator, it really wouldn't show the hole. If you trace to x equals 2, it will certainly show you that there's no value there. So just make a note here that f of 2 actually doesn't even have a value. F of 2 would be the empty set. However, the limit as x approaches 2 does exist. The limit as x approaches 2 is 4, and that will be an important concept in this chapter. All right, moving on to the last technique here. So for the last technique, we have, let's actually just think about what it would look like in a table format. If you go to Y1 at this point and type this into the calculator, let's go ahead and do that. So in y equals, I'm going to type in, you guys know how to do fancy fractions? You know how to do everything on these calculators, but alpha y equals might be a nice way to get you that fancy fraction there. X squared minus 4 over x minus 2. Oh, by the way, let's zoom 6 it. Here's the graph. Yep, it's that line I graphed. It doesn't show the hole necessarily at 2, 4, but we know it's there. What I want you to do is we're going to go to the table setup, second window, and we want to switch the independent over to ask. I'm hoping this is something you're familiar with from Algebra 2 and from pre-calc. But the advantage to this is we can now input whatever x values we want for the independent variable, and it will give us the corresponding y values. Well, what x values do I want? I want x values that are going to get really, really close to x equals 2, like maybe 1.9. And when I input 1.9 for x, the output is 3.9. But can't we get even closer than 1.9? I mean, 1.99 is even better. And I could even go 1.999 if I wanted to, but I think you guys get the idea here. Now, one quick note is that these values are both to the left of 2. We should also check some values to the right of 2, like 2.01. That's going to be 4.01. So you can see, like, as I close the gap here and I kind of crunch down and get closer and closer to x equals 2, the y values are approaching the same thing and getting closer and closer to 4. And in certain cases, it might appear from the left, oh yeah, it's getting closer to 4, and then all of a sudden the right side doesn't match that. So in that case, the limit would not exist. Okay. If you think you're pretty savvy with limits, go ahead and try these examples. You can always hit pause at any moment if I'm going too fast, or if you're like, hey, I think I got this, and move on in the lesson. That's completely up to you. But if you want to follow along for now, let's evaluate these using an appropriate method. So appropriate methods are really, I guess, any of these up here. It doesn't specify if we should do it algebraically, graphically, numerically. I like trying algebraically first to see what happens. In the first example, we're going to get 1 over 0. And 1 over 0 is not an indeterminate form. But you have to be a little bit cautious about this, because I'll tell you in example 3 here, you'll also get 1 over 0, because we're taking both limits as x goes to 0. But example 2 and example 3 have different limits as x approaches 0. So in order to figure out what the limits are, it may be beneficial to actually consider what the graph of these things look like. Let's kind of jump to example 3 for a moment here. Maybe you remember what 1 over x looks like. Okay, it's the reciprocal function it's known as. It's a rational function because we have a fraction with x's in the denominator here. 1 over x is this hyperbola-looking graph. And you'll notice that as x approaches 0, from the left and from the right-hand side, we're really headed to 2 different places. Okay, so in this case, 1 over 0 indicates that the limit as x approaches 0 does not exist. And usually when there is a 0 in the denominator, that's the conclusion. So why is that not the case for example 2? Well, example 2 is a little bit different when we think about the graph. 1 over x squared, we're not going to anticipate seeing any of these negative y values, because the squaring function in the denominator will make this entire fraction always positive. So because of that, we're going to get a graph that looks something like this. I like to think of this as the volcano graph. I don't know. I think of like volcano, lava down here, and then the lava is going to come out, and there's my volcano. But anyway, what's happening here is that as we approach 0 from the left and from the right-hand side, the curves of this graph are headed towards the same value. And what are they headed towards? They're headed towards infinity. So the limit as x goes to 0 for 1 over x squared, we would not define as being does not exist. We would say that this limit is infinite. With definitely a lot more to come on these two cases as we explore some initial concepts with limits. But for now, hopefully those graphs help us to justify this limit does not exist. On the left side, we're headed towards negative infinity, right side towards infinity. Here, they're both going towards positive infinity. So as x approaches 0, that's our limit. Finally, in the last scenario, the limit as x approaches 3. If I plug in 3 to the top and bottom, 3 cubed is 27. So we're definitely going to get that 0 over 0 case. Remember that this is indeterminate. Okay, so we have to do something to figure out what's going on here. In our initial stages here, that something is just going to be to factor. So if we factor the numerator, that's the difference of perfect cubes. So that's going to factor into x minus 3 times x squared plus 3x plus 9. The denominator is x minus 3. We have to have that removable piece there, that removable factor, in order to be able to evaluate this limit. So it turns into the limit as x approaches 3 for x squared plus 3x plus 9. And if you plug in the 3 for all those x's, you're going to wind up getting 9 plus 9 plus 9 for a final answer of 27. If you were to analyze this graph, you would see this quadratic, this parabola, with a hole at the coordinate positive 3, 27. Well, we would put it in there, but calculator wouldn't do the best job showing that. So just some quick limit evaluating to get started here on day one. There's one more case I want us to consider. We're going to look specifically at some one-sided limits as they pertain to the greatest integer function. So I know this is something that would have come up in the summer homework, that September review. So considering the greatest integer function, what would that look like? Let's make a quick sketch over here because that will help us to justify the limits that we're about to write down. So the idea with the greatest integer function is we input integers and the output is the greatest integer less than or equal to what we inputted. So when I input 0, we get 0 returns, but anything from 0 to 1 is going to return a 0. Until I input 1, then the output is 1. But anything from 1 to 2 is going to return a 1. But then when I plug in 2, the output is 2. And you can kind of see the pattern. Same thing would happen on the negative side. Okay, negative decimals like negative 0.5. The greatest integer less than that is negative 1. So we get this, and we get this pattern to continue. I think you're probably familiar with this as being the step function. We very commonly refer to the greatest integer function as. So hopefully you're familiar with this notation here that we're approaching 2 from the right and from the left to get started. So positive sign in that little exponent spot would be as x approaches 2 from the right. So as I approach 2 from the right-hand side, so start on the right-hand side of your graph and head towards 2, I'm following this step right here, and we're getting closer and closer and closer to 2. And then on the other hand, when I start on the left-hand side of my graph and I get closer and closer and closer to 2, I'm following this step right here. So as x approaches 2 from the left, I'm getting closer and closer to 1. So what that tells me at the end is since these right-hand and left-hand limits are different, that the limit as x approaches 2 in general does not exist. So graphically, that has to be true in order for the limit to exist. The limit from the left and from the right must be equal. Okay, so for the greatest integer function, you'll find that the limit will not exist at any integer values. It will exist at non-integer values because as I, let's say, wanted to get close to 0.5. Well, as I approach 0.5 from the left and the right, we're getting closer and closer to 0, so that's fine. But at any integer, you're always going to be off a step from the left and the right-hand sides, so we'll find that those limits do not exist. The last thing that you see at the bottom of the page here is just something that I want you to be familiar with and read through quickly. These are just some properties of limits, that the limit as x approaches a for a constant is just that constant value. If you have the limit of a constant times a function, you can kind of pull that constant out on the outside. So it would be k times the limit as x approaches a for that function. Notice how I've defined up here that the limit as x approaches a for f of x and g of x are a and b respectively. And if you continue down the line, the limit of a sum is equal to the sum of the limits, and it follows for the other operations as well. The limit of a difference is equal to the difference of the limits, the product, and finally, we always know we have to be aware of the quotient because if b is equal to 0, then we get something that's undefined, but otherwise, this holds true as long as b does not equal 0. If you want another visual, these can be found on page 108 in your textbook. And the last thing that I'll say about this intro lesson is that this page right here is really just practice for you. So we have this information here about continuous and discontinuous functions. So what I'd like you to do is try and work on these 4 questions as part of your note taking and we'll wind up going over these the next time I see you in class. So next time in class, we'll start by going over this quickly, and then after we're done going over that, we'll take a look at some additional practice questions. So hopefully you guys have a fantastic day. And in the meantime, if you have any questions that come up, let me know.